I'm going to be talking about a periodic trend called electronegativity, how that determines the bond type, and then what's called the VSEPR model, which is the system for determining any 3D shape of a given molecule. First, let's talk about electronegativity and bond type. So the electronegativity is the ability of an element to attract electrons in bonding. Here's a chart of electronegativity. The numbers range from a low end of 0.7 on the bottom left and a high of 4 on the top right. So fluorine is the most electronegative element on the periodic table, meaning that it has the easiest ability to attract electrons from other elements to bond. So the general trend is that it increases going up and to the right on the periodic table. So it's highest over there and then lowest on the left-hand side. You will have access to an electronegativity chart in class at all times. The general trend is that if you have an electronegativity difference of less than 0.4, then you have what's called a non-polar covalent molecule. If you have a difference of 0.5 to 1.5, that's going to be a polar covalent molecule. And if you have a difference of greater than 1.5, it's going to be an ionic bond. So the definitions of the nonpolar and polar: for a nonpolar covalent molecule, you have 50-50 sharing of valence electrons evenly shared between nonmetals only. Compared to polar covalent molecules, you have an unequal sharing of valence electrons between nonmetals only, and I like to think of it as like a 70-30 share. And then for an ionic compound, you have a metal cation transferring electrons to a non-metal anion to complete an ionic bond. So you have electrons gained and electrons lost with a metal and a non-metal. So just a couple of practice problems, and you can see down on the bottom left this chart. We'll use that as an example. So here's some sample bonds. I have sodium chloride right off the bat. Sodium is a metal and chlorine is a nonmetal. So determining the type of element should be first and foremost. And because of that, I know it's ionic, but we're still going to do the calculations just to make sure. Sodium has an electronegativity of 0.9. Chlorine has an electronegativity of 3. The difference is 2.1. You notice how chlorine's electronegativity came first. The reason why is because you never want a negative number, so you're always going to take big minus little. So a 2.1 is definitely greater than 1.5, therefore it's ionic, but we already knew that because it was a metal and a nonmetal. So that's ionic. The next one, you have two chlorines bonded together as a diatomic molecule, Cl2. So you would take chlorine, which is 3 minus 3 equals 0. So that has to be a non-polar covalent. Carbon and oxygen. Oxygen has a larger electronegativity, so that comes first, so 3.5, and then carbon is 2.5. You subtract them, you get 1. That falls into the polar range. And then C and H. Carbon has a higher electronegativity at 2.5 minus hydrogen at 2.1 gets you 0.4. So that is going to be on the boundary, or the 0.4, so that's a non-polar covalent molecule. We're going to talk about something called a dipole. Dipoles only exist in polar covalent molecules. Oops. Just pull all this up. There we go. So only in polar covalent bonds, and this is created from the uneven distribution of electrons. And what happens is the atoms in the bond actually have a partial charge. Just like cations and anions have charges, well, in a polar covalent molecule, they can also have slight charges or a partial charge. You can determine which has a partial positive charge and which has a partial negative charge by the electronegativity. So if we backtrack to look at the values, chlorine has an electronegativity of 3, hydrogen has an electronegativity of 2.1. Okay, so now that we know that, chlorine has a higher electronegativity, therefore it is doing the pulling of the electrons. So the electrons that are being shared between the hydrogen and chlorine are being pulled closer towards the chlorine because it is more electronegative. So you still have sharing of electrons between the hydrogen and chlorine, but remember that's 70-30. You can think about it as chlorine is pulling 70% and then hydrogen's pulling back at about 30%. So it's totally unequal. Whichever element has the higher electronegativity is the dipole negative. That symbol is like kind of like a music note. It's like the letter S with a swirly tail and then a negative sign, and I'll show you examples later. Whatever has the lower electronegativity, which is doing the 30% pulling, it has the partial positive end. You also can denote it with an arrow with a positive end on one side and the arrow showing the direction of the pole towards the slightly dipole negative side. Okay, so we are going to talk about the VSEPR model. The VSEPR model stands for valence shell electron pair repulsion. That's just a fancy way of saying, how do I create a 3D molecule where the electrons are perfectly placed so that they don't repel each other while simultaneously being attracted to whatever elements in the center and having the electrons evenly distributed among the molecule. Okay, this is based upon a couple of different things. So it's a 3D shape which keeps the electrons, either lone pairs or bonded electrons, as far away as possible. The shape of the 3D molecule depends on the number of bonds and the lone pairs. Both of these are referred to as domains. The domains are attached to your central atom. The letters that we use in this system is A equals the central atom, X equals the bonded atoms, E equals the lone pairs. Again, I'll show you an example. Example is going to be SO2. The first element, sulfur, is going to be my central atom, which is represented by the letter A. And then I have 2 oxygens, which are my bonded atoms, which is represented by the letter X. I need to draw the Lewis dot structure to determine if there are any lone pairs. So sulfur has 6 valence electrons. Oxygen, 1 on either side for symmetry, also has 6 valence electrons. So if there's 3 elements, each with 6 valence electrons, it's a total of 18. I need to make sure I have 18 electrons by the time this is over. So you can see right off the bat, my sulfur only has 6 electrons. So what I'm going to do is steal from one of the oxygens, double bond, and then recount to make sure that I have 18 valence electrons and everything's completed the octet rule. So oxygen, 2, 4, 6, 8, sulfur, 2, 4, 6, 8, oxygen, 2, 4, 6, 8. Total of 18 electrons. So this is your molecule. Right off the bat, the lone pairs are on your central atom only. So this is a lone pair. And remember that lone pairs are given the letter E. Move that over. There we go. So that's denoted with the letter E. So then what I'm going to do is I'm just going to go through and I'm going to figure out what I have. I have an A, which is my central. I have X, and there are 2 of them. There are 2 oxygens, and I have 1 lone pair. So this is what is called your generic formula. The generic formula is associated with a set of properties. Looking on a molecular shapes chart, I'm going to go down and I'm going to figure out where AX2E is. Oh, it's right there. So let's just go through this chart for a little bit. It says in the very first column, total domains, that is your X and your E together. So there are 2 bonded atoms and 1 lone pair. That's a total of 3 things. So I'm in the 3 domain, AX2E, and this tells me how to draw it. So the picture is I'm going to use to redraw my, my Lewis dot structure in an actual molecular geometry structure. It tells me that I have 2 bonded atoms, I know that, with 1 lone pair, and then this tells me my shape. So the shape is going to be bent when I draw it, but the electron geometry is going to be trigonoplanal. The difference between molecular geometry is what it looks like without really taking into consideration the lone pair, so you just have a bent molecule, and then the trigonal planar, tri meaning 3 sides, shows that you really have something that's 3-sided because you have that lone pair. And we're going to skip the hybridization column, but going over into the bond angles, the last column, it tells me that my X's, or my, in this case, my O's, my oxygens, are going to be 120 degrees away from each other. So let's put all that together. So I'm going to redraw with sulfur as the central, and then I have the 2 lone pairs up top, and then I'm going to draw exactly like the picture showed it with the oxygens down below, and they still keep their electrons on the outside to show their octet rule being completed. So this is what it's going to look like, and then this bond angle right here, as it told me, is 120 degrees away from each other. Remember that these oxygen atoms want to be as far away from each other as possible, but trying to maintain a balance with the attraction of the sulfur. But this lone pair, which is kind of given a teardrop, forces the oxygens away, which is what gives it its bent shape. So this is bent as the molecular geometry, trigonal planar as the electron geometry, with a 120 degree angle between the oxygens. Lastly, let's figure out the dipole. So we need to figure out if this is polar and nonpolar. So let's go back to an electronegativity chart. And sulfur has an electronegativity of 2.5. Oxygen has an electronegativity of 3.5. And you notice that there are 2 oxygens. So sulfur is 2.5 and oxygen is 3.5. So really, this oxygen is 3.5 and then this is minus 2.5. That's an electronegativity difference of 1 on that side. And then you also have the same thing over here. So you have 3.5 minus 2.5 equals 1. So it doesn't matter that there's 2 oxygens. The electronegativity is going to be 1 no matter what, which is a polar covalent molecule, electronegativity difference of 1. And then oxygen has a higher electronegativity, therefore it is the dipole negative. So I'm going to give the dipole negative because it's pulling harder. So remember that polar is the 70-30. And then this oxygen is also dipole negative, and then the sulfur is going to be dipole positive. And another way to show that is the arrow pointing towards the dipole negative, and it's going to point towards both of the oxygens. So technically, this is a complete 3D molecule showing polarity. We're going to do one more quick example. We're going to use silicon tetrachloride. Silicon is my central, so that's A. This is my X, the bonded atoms, and I need to draw it to figure out if there are any lone pairs. Silicon has 4 electrons, 1, 2, 3, 4. It's in group 4A. I'm going to bond a chlorine on all 4 sides, and they each have 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I'm going to turn the central connections into lines, and it looks like everything has completed the octet rule. and there are no lone pairs. So the formula for this is AX4 because there are 4 bonded atoms. Going back to the molecular geometry chart, I'm going to look for AX4. Oh, it's right there. Tells me there are 4 domains, meaning there are 4 things attached to the central element. This tells me the geometry, so I'm going to redraw my molecule to match that picture. And you notice how the front X has kind of a darker shaded line, and then the back X has kind of a faded line. That's really important, and I'll show you what that looks like. And then it has 4 bonded atoms, 0 lone pairs. It's tetrahedral for both the electron geometry and the molecular shape because there are no lone pairs. So tetrahedral means 4-sided, and then if you look over the bond angles, the bond is 109.5. So let's put that all into practice. So I have silicon, and what you do to show a 3D shape on a piece of paper is you draw a wedge, a colored in wedge, to show that the chlorine is coming out at you, and then a dashed line to show that a chlorine is going back. And then there's going to be a chlorine over here, and then a chlorine up here. Okay, and then the bond angles are all 109.5 degrees away from each other, all of them. Let's figure out if this is a nonpolar or polar covalent molecule. Let's go back to a polarity or electronegativity chart. So silicon is 1.8, chlorine is 3. That is an electronegativity difference of 1.2. Therefore, this is polar. Chlorine has a high electronegativity. Therefore, it is the dipole negative. So the chlorines are all going to get dipole negatives. And the silicon, is going to get a dipole positive. And then you have the arrows showing the pole towards the dipole negatives. And again, this is tetrahedral for the molecular shape and tetrahedral for the molecular geometry. And that's it.